Hello, my name is Harry Chen, and I will be covering polynomial interpolation. So before we continue, we need to figure out what exactly polynomial interpolation is. So let's say we have endpoints. We have endpoints. We will label these x1, y1, that's the first point. And then x2, y2, that's the second point. And then we just keep labeling them like this until we get to xn, yn. So we have, these are our endpoints. So we want to find a polynomial of degree n minus 1 or less, so n minus 1 is greater than or equal to the degree of the polynomial. And this polynomial is special because all of the endpoints above, they have to be on this polynomial. So importantly, of course, these x-coordinates have to be all different or else you can't have a function. So we'll say all these x-coordinates are different. And yeah, so turns out there both exists such a polynomial that has all these points on it, and that polynomial is unique, so there are no other polynomials that work. We will prove both of these results later, but for now we'll just take those to be granted. Take those for granted. So, I guess as an example, let's say we have the points 1, 1, 2, 3, and 5, 6. These are 3 points, so replace n with 3. Then we want to find a polynomial of degree 2 or less, such that all 3 of these points are on that parabola. So as it turns out, this polynomial is minus 0.25x squared plus 2.75x minus 1.5. So just I'll show how we find this polynomial in the next section, but for now this polynomial is the unique polynomial that has all 3 of these points on it. And you can do that calculation yourself if you want, but you can also just trust me that these three points are on this polynomial. Here's what it looks like. Here's what these 3 points look like on that polynomial from that last slide. And so, yeah, so now I'll show you one method at least for finding this polynomial. Of the 2 methods I'll show you in this lecture, this one's probably the easier one to understand and the easier one to memorize. And so basically, since we know the degree of the polynomial is n minus 1 or less, so n minus 1 is not greater than or equal to the degree, we can just write the polynomial with some variables as the coefficients. So we know that p of x is in the form a0 plus a1x plus dot 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 plus all the way up to a sub n minus 1 times x to the n minus 1. So this is a polynomial of degree n minus 1 or less, because if a sub n minus 1 is 0, then of course the degree is less. But so we know the polynomial has to be in this form, so now we can just solve for the variables. In order to solve for variables, we need some equations. So we can just exploit the fact that all of these endpoints are on the polynomial. So by definition, this is true. P of x sub k is equal to yk for basically all k. So that just means that all of the points are on the graph. That's what it means mathematically. And so as it turns out, we have, for each point, we have one of these equations. And then, yeah, so we can use these equations. They all have, all of the unknowns are a0, a1, all the way up to a sub n minus 1, and then they're n equations. So I guess one thing important to note is that we have n variables, right? Those are all the a's. And then we also have n equations. So since we have as many equations as we have variables, we can actually solve for the variables. I guess the keen of you watching might ask why. The keen of you might say that maybe the system of equations, they have no solutions, or maybe they have infinite solutions. But again, just take for granted that such a polynomial exists and that such a polynomial is unique. And if we take that to be true, then this system will always have a solution, and there will never be like more than one solution. So yeah. And so after we solve this system, we get all the coefficients, and then we just substitute that back into the form up here, and that's our polynomial. So let's give an example. Yeah, so this is the same points as before. Use the system of equations method to interpolate the points 1, 1, 2, 3, 5, 6 with a polynomial of degree of 2 at most. So that's just what interpolating is, or polynomial interpolation is. Yeah, so let's just use the formula from the last slide. We have that from the first point, 1, 1, we have that 1 is equal to a0 plus a1 plus a2. From the second point here, we have that 3 is equal to a0 plus, not a1, but it's actually 2a1 plus 4a2, because that's 2 squared. And then from the last equation, we have that 6 is equal to a0 plus 5a1 plus 25a2. And yeah, so now we can just do some equation manipulation. From these two, we get that 2 is equal to a1 plus 3a2. And then from these two equations down here, we get that 3 is equal to 3a1 plus, oops, 3a1 plus 21a2. We can multiply this top equation by 3, and then subtract the two equations, and we should get something like minus 3 is equal to 12a2, which means that a2 is equal to minus 1/4, or minus 0.25. And so I'm not going to spare you the details. The other a1 is equal to the a1 is equal to 2.75, and then a0 equal to minus 1.5. You can find this pretty easily from the equations. I'm not going to show you how, but yeah, this is just what you learned in your algebra class, presumably. And so in all, since we have all three unknowns solved for, we just get that the polynomial is minus 0.25 x squared plus 2.75 x minus 1.5. This is just the same results that we had from last time, that I gave you before, which is good. That should be what we expect. So this method works. However, with the system of equations method, there are a few issues. The biggest one is that it is very time consuming to use because you have to solve an entire system of equations to even get your polynomial. That can be troublesome, especially when you're given a large amount of points. Like if you have 6 points, then that means you have to solve a system of 6 equations. And that is, that's just tedious. That's very tedious, that's very slow, you don't want to do it. So typically, you would leave that to the computers, but yeah, if you want to do it, but for the sake of problems and stuff, we have the Lagrange method of interpolation. And so this one is special because it just directly gives you a formula for the polynomial, and so you don't have to do any extra work of solving for coefficients or solving for the polynomial itself. You do, this one is a little strange, but you'll see that in a second. So let there be n points, yeah. Then there exists a polynomial p of x of degree at most n minus 1 such that p of xk is equal to y sub k, where all 1 is less than or equal to k is less than or equal to n. That's just what interpolation is. So, but here's the meat of it. This polynomial can be written as p of x is equal to the sum from j equals 1 to n of y sub j times the product of x minus xk divided by xj minus xk, as k ranges from basically k ranges from 1 to n except for when k is equal to j. So that's just what this here means, the x is not equal to j. Yeah, and so here's why this equation works at interpolating. So just let xm be one of the endpoints. Just let it be one of the endpoints that we have above. So if we want to calculate p of xm, so first notice that most of the terms of the sum actually just cancel out because we have up here in the numerator we have x minus xk, where k ranges over everything except for j, And so because of that, at some point in a lot of them, we're going to have x minus xm, and when we plug in xm for x, we just get 0. And so when the product, so the numerator just becomes 0 because 0 times anything is 0, and so that entire term just gets reduced down to 0. So there's actually only one part of the sum that is not reduced to 0, and that's when j is equal to k, because when j is equal to k, there won't be an x minus xm term. There just won't be. So we just got to figure out when k is equal to j. That's just what we have to care about. And so here we can just substitute in k for j, and we get, or j for k, it doesn't really matter, but we get that we get y sub. Oh, sorry, not k is equal to j. It should be j is equal to m. Sorry. When j is equal to m, k will never equal m, and so there will never be x minus xm. So when j is equal to m, let's substitute this in. We get inside of the sum, we get y sub m times the product when k is not equal to m of x minus xk divided by xm minus xk. So when we substitute an xm, this just becomes xm minus xk in the numerator, and down here is xm minus xk in the denominator, so this just cancels out, becomes 1. And so this is just the product of a bunch of 1, so that's just 1, so we're really just left with ym. And so we have that p of xm is equal to ym for all xm. And so that just means that interpolates all the points. That's what we want. And there are some other things we need to check. We need to make sure this is indeed of degree at most n minus 1. That's true though, because in the numerator we only have n minus 1 of these terms being multiplied by each other, so the degree can be at most n minus 1. Additionally, we have to make sure there's no divide by 0 errors, but that's actually handled because we know that all the axes are distinct. That's one of the things that we specified. And since k can never equal j, we'll never have an xj minus xj situation down here, and so we should be clear in that. So this does indeed work. This also improves the existence of an interpolating polynomial because, well, we have a formula for it. If the formula always works, then that means it always exists. So it's true it exists by construction. Now we'll show it in action. Use the Lagrange method, to interpolate the points 1, 1, 2, 3, and 5, 6 with a polynomial of degree of 2 at most. So let's just use the formula. P of x is equal to 1 times x minus 2, so that's the second point, divided by 1 minus 2 times x minus 5 divided by 1 minus 5 plus, so now we're going to go to the second point, 3 times x minus 1 divided by 2 minus 1 times x minus 5 divided by 2 minus 5 plus 6 times x minus 1 divided by 5 minus 1 times x minus 2 divided by 5 minus 2. And so this is our polynomial. Even though it doesn't quite look that clean, it is actually our polynomial. Now if you want to put it in standard form, that's pretty easy, albeit tedious to do. You have to do a whole bunch of expansions and all of that, but you can just trust me that this is indeed equal to what we had before. This is equal to 0.25 x squared plus 2.75x minus 1.5. So these are actually the same. Trust me. And so this just shows that the Lagrange method works. It produces a polynomial that fits the bill. However, the Lagrange interpolation is not only useful for finding the polynomial, we can use it for problems. So let P of x be a polynomial of degree at most 1009, such that P of n is equal to 2 to the n for all integers from n is equal to 1011 to 2020. And P of 2021. So our points here are just going to be It's going to be 1011, 2 to the 1011, that's 1 point, and then just so on like that until we get to 22020, comma 2 to the 2020. So I already told you we're going to be using Lagrange here, so let's just do it. Let's put this into the formula. So P of x is equal to the sum from j equals 1011 to 2020 of 2 to the j times, so now instead of doing the product, and we're just, instead of doing k is not equal to j, we're actually just going to split it up to when k is less than j and when k is greater than j. So the first product is when k is less than j, so it starts at k is equal to 1011, and it goes until j minus 1. So right before it hits j, and then inside is just x minus k divided by j minus k. And the second product is after the j, so it's just at k equals j plus 1 and goes until the end, so that's 2020. And this is also of x minus k divided by j minus k. Good enough. So because all the x values are consecutive, I'm just gonna I just use j is equal to the x values directly instead of instead of just using them as indices. So instead of doing x1, x2, x3, I just did 1011, 1012, 1013 directly. Just makes it easier. And so this is our polynomial. It's we do not have to simplify this, and I actually implore you not to. It's just way too large. So instead, we're just going to directly plug in 2021 because that's what we want. We don't want the polynomial. We just want what it is evaluated to 2021. So let's do that. Okay, wonderful. So this looks daunting, but we can handle each product separately. So let's start with the rightmost one. So if we just write out some terms, let's just write out some terms actually. So the first one is 2020 minus j divided by -1 times 2019 minus j divided by -2 times all, we'll do dot 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 here. So when k is equal to 2019, we have 2 divided by j minus 2019. And then when k finally reaches 2020, we have just 1 divided by j minus 2020. So yeah. So there's something interesting here because over here we have a -1, and up here we have 1. Down here we have -2, up here we have 2, and then down here we have j minus 2019. Up here we have 2019 minus j, then j minus 2020, then 2020 minus j. So it turns out that each one's actually the numerator. Each term in the denominator has a corresponding term in the numerator, just multiplied by -1. So by symmetry, we can actually just cancel all of them out. So we can cancel this. We're actually just left with -1 after that. So cancel, 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 cancel. So each one of these only contributes a -1. So actually, this turns out that this product is actually just equal to -1 to the power of j. Yeah, it's roughly equal to, it's just equal to j, -1 to the power of j. And so, okay, so we simplified that product. Let's go to the second product. Second product, we have 1010 divided by j minus 1011 times 1009 divided by j minus 1012, and then dot dot dot, and yeah, after the dot 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 we should have 2022 minus j, I believe. Yeah, divided by 1. Yeah. So yeah, so this is interesting. So it turns out that this is actually just equal to 1010 choose j minus 1011. And why might this be? It's because in the denominator here, this denominator turns out is that's just equal to j minus the factorial of j minus 1011. So this is just j minus 1011 factorial. And then up here, we should have, and so up here we actually have 1010 factorial divided by yeah, it should be that divided by j minus, yeah, I'm sorry, it's not j, it's sorry, it's 2021 minus j factorial. So put these together, it actually turns out that this is precisely equal to 1010 choose j minus 1011. So that's pretty cool. And so we can put this together now. Here's a new slide. When we put this together, we actually get that P of 2021 is equal to j is equal to 1011 to 2020 of 2 to the j times 1010 choose j minus 1011 times -1 to the jth power. So we can now we can actually we can make it so the summation starts at 0 instead of 1011. So just shift it back a bunch. So the summation of j equals 0 to 1009, I believe. And so we actually have to be careful for a few things. So for number one, we actually have to, it actually becomes 2 to the j minus 1011, sorry, j plus 1000, 1011 times 1010 choose j times -1 to the power of j plus 1011. We can actually move the 1011 outside of this. We don't want that. Probably want everything to be in terms of just j. So this actually becomes -2 to the -2 to the 1011th times all of this. And so we can also combine together the -1 to the power of j and the 2 to the j to just get -2 to the j. And so here's what we're left with. We're left with the sum from j equals 0 to 1009 of -2 to the power of j times 1010 choose j. So this is quite close to the binomial theorem. It is very, because the binomial theorem is the sum from, well, it would be the sum from j equals 0 to 1010 of -2 to the j times 1010 choose j. And so all we have to do is we just have to account for the 1010. So this actually is equal to we can, yeah, so this is equal to 2 to the 2021 minus 2 to the 1011 times j equals 0 to 1010 of -2 to the j times 1010 choose j. And so essentially we added a term for when j is equal to 1010, then we subtracted out the term as well, so it's a net change of 0. And then when we brought that out, so when we plug in 1010 for j, we get -2 to the 1010, so 2 to the 1010 times 1, since 1010 choose 1010 is just 1. And then we can bring that out, and that's where we got the 2 to the 2021 from. So now applying the binomial theorem, this is just equal to 1 minus 2 to the power of 1010. And so that's just equal to 1. So this entire summation here is just equal to 1. That's all I had to do. So all we're left with is 2 to the 2021 minus 2 to the 1011. That's quite nice. And so yeah, this is our final answer for what P of 2021 is. So yeah, so that's how you can use Lagrange interpolation for this problem. there's actually a whole host of problems similar to this. Knowing the identity that you can actually, knowing the identity when you have the summation from like, 1011 to 2020 or something like that, just consecutive integers, and you have a function for that polynomial across those integers. It actually produces a choose each time, so that's good to know, especially if you see a problem like this ever again. You can even do it in reverse. Yeah, so it's quite a versatile tool. All in all, there's other applications for Lagrange interpolation. It's used in it can be used to interpolate a piece of just data that you have and get a good estimate for it instead of getting like the direct value. But yeah, well, we will not be showing that today. That's not typically used in math competitions. So, but that's Lagrange interpolation. Now we have an optional part. This part is about proving why this interpolating polynomial is unique. We already showed why it existed, but now we got to show why it's unique. Yeah, so existence and uniqueness. Let there be n points, then there exists a unique polynomial p of x of a degree at most n minus 1, such that p of x k is equal to yk for all 1 is less than or equal to k is less than n. So that's just what interpolating is. So this proof is going to be a proof by contradiction. So let's say there's another polynomial. Let's say there's another polynomial q of x that also interpolates the points, right? And this polynomial is not equal. It is not equal to p of x, so they're not the same. So then let's define another polynomial. Let's say it's called r of x that is equal to p of x minus q of x. So since p of x is equal to q of x at all of these n points, because they both interpolate the data, the points, we know that r of x has roots there. R of x is equal to 0 at x equals x sub k. And so this means that there's and so this means that there are at least n roots of r of x, right? And so because there's at least n roots, that means this must be a polynomial of degree at least n. So the only issue is that when we actually subtracted these, since we're only subtracting them, we're not like multiplying them or anything. That means the degree of r of x here has to be less than n. Has to be a degree less than or equal to n minus 1, because we know that both q of x and p of x have a degree less than or equal to n minus 1. But these two can't be true simultaneously. R of x can't have a degree of more than n, but it also can't have a degree of less than n. So, sorry, it can't simultaneously have a degree of at least n, but also a degree of less than n. So this is a contradiction. So therefore, q of x doesn't exist. There is no other polynomial that interpolates the data. So we already showed that existed. So p of x does exist, and it is the only polynomial that interpolates the data. And so that is it for the polynomial interpolation lecture. Yeah, there's actually another way to interpolate data, to interpolate points using a polynomial, and that uses finite differences. However, that method's kind of limited because the points have to have consecutive x values for the most part in order to use it, in order to interpolate it effectively or efficiently at the very least. But yeah, if you want to see that, you can look that up, or you can check out our past lecture on finite differences. Yeah, I'll put that in the description. So thank you for watching, and good luck on your mathematical endeavors.